Welcome, and thank you so much for tuning in. We're pleased to have you join us for this Interagency Working Group on Ocean Acidification webinar. The title of today's presentation is CO2 Systems Studies in Brackish Waters. What should I measure and why? This webinar is hosted by the Interagency Working Group on Ocean Acidification, a collaborative working group of 13 federal agencies that aims to coordinate and foster federal research and monitoring on ocean acidification. The group is chaired by Libby Jewett, Director of NOAA's Ocean Acidification Program. By hosting webinars, the Interagency Working Group on Ocean Acidification hopes to build the nation's capacity to work on ocean acidification and the community of people doing so. I'm Shallon Bush, an ecologist with NOAA's Ocean Acidification Program and Northwest Fisheries Science Center in Seattle, Washington. I staff the Interagency Working Group on Ocean Acidification and will be monitoring today's session on behalf of the group. Jen Bennett-Mintz, Education and Outreach Coordinator for NOAA's Ocean Acidification Program, is also on the line and will be helping to facilitate today's session. During the presentation, all audience members will be in listen-only mode. You are welcome to type questions related to technical issues or for our presenter in the questions box in the bottom of the control panel on the right side of your screen. We'll monitor incoming questions and respond to them or pose them to our speaker. We are also recording this session. A video recording of the presentation will be available in the future and linked to on the group's website. We're very excited to welcome our speaker, Dr. Andrew Dickson. Dr. Dickson received his PhD at the University of Liverpool in the United Kingdom in 1978, studying acid-base chemistry in seawater. After a postdoctoral fellowship at the Marine Biological Association Laboratory in Plymouth, modeling chemical processes in estuaries, he moved to the University of Florida to work on a project aiming to define pH in seawater. In 1983, he moved to the Scripps Institution of Oceanography at UC San Diego, where he is now a professor of marine chemistry. His research focuses on improving our understanding of the CO2 system in seawater, with a current emphasis on the effects of ocean acidification. And with that, I'm going to pass the presentation over to Andrew to begin.
Hello and welcome. The title, you heard in my brief introduction there my actual short exposure to estuaries at all as a postdoc modeling them. So bear that in mind as we go through this talk. I may not know as much as you do about the everyday problems involved in doing this. What I'm looking to do is give you some feeling as to the chemical basis of the kinds of problems you will have in analyzing brackish waters and also in understanding how you can use programs like CO2 sys or CO2 calc to compute other aspects of the CO2 chemistry of brackish waters. So just to start, the word brackish is not very clear. It's not fresh water, it's slightly salty. I've been a little bit sort of cavalier with this, and I'm imagining it as the sort of range of salinities that you might find in areas where you would definitely not call it ocean water. So when you have this water, which is essentially, as it points out here, partly fresh, partly salt, you have a couple of things to worry about. There are two separate issues. First, you need to understand the assumptions that govern the acid-base chemistry in brackish waters and how people talk about it. And second, you need to be able to measure sufficient information to define the state of the CO2 system in such waters with an appropriate uncertainty. Now, throughout this talk, I will have text in this sort of brown font. It's to remind you that these are somewhat qualitative terms. They're not clearly objective statements. What is sufficient information? What is an appropriate uncertainty? We will try to discuss some of that going on, but really what this means is I can't answer the question, what should I measure and why? I can give you an idea of how you should think about that. And that's really how this talk is going to go. So, as we talk about the acid-base chemistry in aqueous mixtures of electrolytes or salts, and really all black brackish water is such, and seawater as well, I'm going to give you an idea of what's going on there and how it differs potentially from thinking about seawater itself and normal ocean thinking of the CO2 system. So, an equilibrium constant. You can have an acid-base dissociation. Here, some base B, the acid HB dissociating. There's a standard equilibrium constant. Those of you fortunate enough to have done physical chemistry will not be too horrified at this. If you are fortunate enough not to have done physical chemistry, then I'm afraid the next few slides might be more exciting than you want. But the essence here is that there's this product between a term which is based on concentrations, the ones with the square parentheses around, square brackets, and activity coefficient term. And the constant here is a function, is what's referred to as a thermodynamic equilibrium constant. It's a function of temperature and pressure only. The activity coefficients are a function of temperature, pressure, and the solution composition. Now, in this expression, I put square brackets because that's what I'll use throughout to mean moles per kilogram of solution, which is the normal seawater practice. But, of course, you will see this with concentrations as moles per liter, concentrations as moles per kilogram of water, and doubtless other possibilities exist as well. They're just less common. So we can rewrite this for simplicity in future equations as a product between that term in concentrations and this term in red, the capital gamma, being that composite activity coefficient term, which, as I said, depends on temperature, pressure, and the solution composition. Now, if you're going to use an equilibrium constant, you are looking to calculate how much is present as an acid, how much is present as a base. So if you know the total concentration, and you can measure a pH, and here I've written it as a hydrogen ion concentration is 10 to the minus pH divided by some arbitrary constant C. C itself is a function of temperature, pressure, composition, and it depends how pH is defined. Now, to those of you that this is completely new, I point out that I covered this idea in a webinar about 2 months ago, and I believe that webinar will shortly become available for public viewing, and so you can go back and think about this. But in essence, what you're saying is that if you want to talk about hydrogen ion concentration and you want to measure something you're going to call pH, you need to know the relationship between those two. In an ideal world, the number C would be 1, but it often isn't. So you can then calculate the individual concentrations for the base and for the acid. And to do this, you need to know lots of things. You need to know the pH and that value for C, the total concentration of your base, the equilibrium constant, and the activity coefficient term. Now, how do you get an activity coefficient term? Well, you can use equations that look like this, where you need the complete composition of the solution plus all the parameters. Now, before you look at that and go, oh my God, actually perhaps while you're looking at that going, oh my God, if you look carefully at any one of those terms, you will see that it's a sum of a product of some parameter and concentrations here in moles per kilogram of water. And so all these activity coefficients come from those interactions. Now, probably you'll be going, just a moment, surely seawater was never this complicated. And the answer is not usually. because convenient simplifications exist for seawater. In oceanic seawater, two things hold true. First, the acid-base species are minor constituents. Now, that means that in these sums, you can pretty well ignore them because they're weighted low because there's only small concentrations, and the interaction coefficients are about the same for all the species. They vary somewhat. So you end up saying, we don't need to worry about the acid-base species in this. And in seawater, and this is the big key, the amounts of the major constituents are salinity dependent. So we end up essentially that activity coefficient term is a simple function of salinity, temperature, pressure. So suddenly this picture just disappears and we say, okay, we've got a term that's just a function of salinity. So in seawater we define a stoichiometric constant, that is a constant that's just in terms of concentrations, and you can see that that is related to what we've talked about before. But if that activity coefficient term is a function of salinity, it's built into the constant in that way. You can also hide that value for C. We see here that the ratio of the base and acid forms is dependent upon that stoichiometric constant, and the hydrogen ion concentration, 10 C. So ultimately, you can include that C in the constant as well. And seawater constants are of this form. They are defined in terms of concentrations, but maybe the hydrogen ion is really just 10 to the minus pH. We try to make it a concentration. There are varying concentration scales, and again, for more detail, go back to my previous webinar. But the takeaway message here is if you define pH in a different way, then the K star value here changes its value. So in oceanic water, we define these constants that are functions of salinity, temperature, pressure, and then it's straightforward to do that same speciation calculation. In brackish water, there are two problems that need to be considered. On your lucky day, you can say, I don't care. It doesn't matter enough. But on an unlucky day, it might be different. First is, as the salinity is reduced, and thus the amounts of the major ions are reduced, at what point is the approximation that changes in the concentrations of acid-base species has no effect on the activity coefficient term? When does that stop being sufficiently true? Notice the brown again. And second, brackish water is normally a mixture of seawater with a river rather than pure water. And a river has its own dissolved components that exist in different proportions to those in seawater. So at what point is it no longer appropriate to assume that the composition can be meaningfully represented, again in brown, by a single composition variable, salinity? It really depends how carefully you want to do this arithmetic, and second, how far your river really is from pure water before part 2 matters. But for a rule of thumb, the number that I would have in my mind is of the order of salinity of about 5. Above a salinity of 5, it probably, neither of these are that important to you. Below, they could be. Functions for K star produced by marine chemists ignore these problems. So you will see this, and I just copied this out of a paper, giving the form of equations, and essentially we're saying, as we did before, that the K star is a term in temperature and salinity, where here there's the zero salinity term is that equation 14, with salinity equal to 0. It's just 1 point, but the A's are also in fact temperature functions of temperature. So here's a set of data like that. This data set from Milero et al. In 2006 covers the widest range of salinities of all published data. Most ocean chemists really have not gone below a salinity of 20. And so these go well down. Salinities, look, this was done, these measurements were done in natural seawater from the Gulf Stream, but they were diluted with deionized water before doing the experiments. And so these really are taking natural seawater and diluting it with pure water. The problems in the shaded region are, come back to that applicability of stoichiometric constants that I talked about before. I don't really have a clear idea from Milero et al.'s paper how much that might matter. It really ends up that you would end up with less well-defined constants in the way that they did it. But as I said, not necessarily so badly defined that they're still not adequately useful. A bigger problem is the difficulty in extrapolating to the zero salinity. The values are quite well known at zero salinity, really quite accurately known. But the shape of that line is not known at all. And as you can see, there are some significant extrapolations going on. And small differences, when the lines get that steep, will result in substantial errors in the likely value of the constants. Ultimately, as I mentioned, if you're in places with significantly different freshwater compositions, this is the region where that may have an effect for you. It's not been carefully studied. In reality, probably you have to go back to those horrifying page of equations that I displayed before to look at the likely magnitude of such effects, and people have not really done that yet. So how good are these constants? What's the likely uncertainty? Well, Milero et al. Show their data against other data. The top panel here is against for K1. They've got a variety there from different measurements, all made in seawaters of varying kinds, synthetic seawater and natural seawater. And you see a reassuring bunch of scatter around the zero line, which is defined by their measurements shown in the previous graph. But clearly there's noise and there are differences between these groups, and it's hard to say. If you look at the K2 version, we're down now to two sets of data. The paper doesn't really seem to discuss quite why this is, but my own prejudice is if you put all those other data on, there would be a lot more scatter, and it wouldn't look as pretty. So my take-home thing is, what's the likely uncertainty? Well, it's hard to tell. But at salinity about 20, my thought is it's about 0.02 or so. That might be a little bit conservative, but I fear probably not too conservative. At salinities less than 5, it could be perhaps as large as 0.1 in the pK. To give you a feeling, 0.02 is about 5%, 0.1 is about 25%. If 5% matters for your calculations, you are always going to have problems. If 25% matters for your calculations, well, you need to worry if you're interested at the low salinity end. So let's move to talking about the measurements. Total dissolved inorganic carbon, essentially the sum of the concentrations of the inorganic carbon species, termed as temperature and pressure independent, usually in micromoles per kilogram of solution. And I'll point out here that direct measurement techniques would not really be, should not be affected by the salinity of the water. So let me explain what I mean by a direct measurement technique. I mean that you have acidified the CO2, acidified the sample, thus essentially turning all these species into the unionized CO2 form, and then you're in some way removing that CO2 from the solution and measuring how much there is. A lot of ways of doing this exist. There are vacuum extractions, terribly tedious, really quite precise. The much more common one is you strip with a gas that has no CO2 in it, and it goes through an infrared analyzer, and you integrate the signal to get the total amount of CO2. Another option is the CO2 is dissolved in a liquid in a device that people refer to as a coulometer, because we're then going to titrate the changes in that liquid to try and estimate how much CO2 was there. Other is the CO2 goes through a membrane and is measured somewhere else. So all these direct measurement techniques where we acidify and separate the CO2 from the solution in some way will work fine over all salinities. You will still get a sensible estimate of total carbon. And probably it would be okay to use our CO2 and seawater reference materials to quality control these measurements, because those two should simply tell you how well your system is working, and don't need to be matched in salinity to really judge how well it's working. For partial pressure of CO2, we're essentially looking at an equilibrium between the gas and aqueous phase, where partial pressure is this product of the mole fraction of CO2 in the gas and the equilibration pressure. This is a temperature and pressure dependent term, and it's usually measured in microatmospheres. But again, the direct measurement techniques, by that I mean that you're equilibrating an air sample with your water and measuring how much CO2 there is now in the air, should not be affected by the salinity of the water. You will get a measurement of PCO2. Other techniques involve having a membrane and the CO2 passes through, and that will be somewhat affected by the salinity of the water, but probably not a lot. It comes back to how big a problem you have, but I'm not aware of how scrupulously those devices have been tested over a range of different salinities. The biggest problem I feel with many of these devices, particularly the ones that are relatively cheap and convenient, is that quality control of how good you're doing is not so easy. And you need to think, what is the likely uncertainty on my PCO2? Because you're going to want to know that. For pH, again, the discussion I've talked about how pH is defined and calibrated. But at this time, the problem is it's not possible to calibrate pH measurements well at salinities less than 20. There has been insufficient work. Now, strictly, what I mean by that is that the way we define the pK values that I've talked about and the way pH gets measured at salinities below 20 are not really defined in the same way. And so that divergence between the pH and the pK ends up as an uncertainty, which you can either call an uncertainty in the pK or an uncertainty in the pH. It really doesn't matter. People are now trying to improve on this situation, but it hasn't happened yet. Alkalinity. Well, alkalinity is a sort of form of mass conservation relationship, rather elaborate definition, whole range of possibility of items that could be in there. It's a CO2 parameter in part because the ones in red dominate this expression for natural seawater. Though some of the other terms are still important in open ocean seawater at the surface, and others becoming more important deeper down where levels of total phosphate or silicate increase. The ammonia and bisulfite really require you to have a more anoxic region. So successful use of this parameter requires that you can calculate all those parameters in black, either with a low enough uncertainty or that you can neglect them. So let's look. Well, borate and fluoride, the total amounts are assumed to be proportional to salinity. In many brackish waters, this is likely to be a very good approximation because the water doesn't have, the fresh water doesn't have high amounts of boron or fluorine in it. If, on the other hand, it does, then that falls apart a little bit. The nutrient species, realistically, you either need to measure them, or if you know they're low, you can ignore them. So again, this brown, if significant, how well do you need to make a measurement? Because it's going to, ultimately, you're trying to calculate the term in red. Now, the real bugbear for many brackish water people is to worry about the terms that we didn't even write down chemical formulae for. The ones I have with ellipses, the dot, dot, dot. And the largest concern is usually organic acids and bases. Because people have shown that there can be organic acids and bases in seawaters, particularly seawaters that are not being quickly mixed into much, much larger amounts of seawater, in bays, in rivers, particularly, you know, people have shown them coming from rivers where you can look at the water and it's clearly a sort of deep color, which isn't just particles in the water, and that's usually organic acids and bases present. If these are present in significant amounts, alkalinity is not a useful CO2 parameter, though it may be of geochemical interest. That is, you can look at the total alkalinity and see how it changes. So, again, we come back to what's a significant amount. If you want to be able to calculate all the non-red and get the alkalinity within 5%, then ignoring, you know, 1 or 2% of organic acids and bases, that is 20 to 40 micromoles per kilogram, wouldn't really be a problem. But you have to figure out how much there is there before deciding that it's necessary to just ignore alkalinity or necessary to ignore acids and bases, and you've already got too much information at that point. So it's a little bit difficult. We can maybe talk more about this in questions. Of course, you can use CO2 and seawater reference materials for quality controlling the alkalinity measurement, and you could even test for a lower salinity water by taking our reference material and diluting it by weight with deionized water to get yourself a lower salinity, which you can calculate because you've just diluted by weight, and a lower alkalinity. You would calculate that as well. And it would tell you that your equipment was also working at a different salinity. But it won't help you identify whether these organic acids and bases are present in significant amounts. So, some closing thoughts. There's a variety of prejudices common in our field. Unreasonable, preconceived judgments or convictions. First, an implicit belief that the strategies developed to make the study of CO2 system or ocean water manageable can be applied to brackish waters without further thought. We've talked about the potential problems with equilibrium constants as you go to lower salinities. We've pointed out that if there's significant organic amounts present, which largely in ocean water we ignore because they're typically low, often below 5, but in brackish waters they need not be low. You need to think about that further. So you can't just say, hey, if I can do all these measurements great in seawater, I can just move straight into any old salinity and get on with it. That's not true. The problem with pH is often you can get a perfectly good precision. But the precision doesn't tell you enough, because the most useful measure when you're going to do calculations with pH, and realistically, why else would you even measure pH if you weren't planning to do such calculations? It's related to how well the pH itself matches that implied in the equilibrium constants you used. And as I mentioned, the problem we've got is as you go to lower salinities, that's not yet so well defined. And one last thing that I'm going to discuss a little bit more, which is a belief that high quality means low uncertainty when you think about seawater CO2 measurements. And we'll just talk a little bit about high quality. It's fitness for purpose. That is, it says here, the property of data produced by a measurement that enables the user to make technically correct decisions for a stated purpose. So it's the magnitude of the uncertainty associated with the measurement in relation to the needs of the application area. In open ocean waters, particularly if you're looking to see how much it's changing due to, let's say, CO2 going into the water from the atmosphere, which is of the order of, about 1 micromole change in total carbon per year, you really do need a low uncertainty for your measurement. But if you're looking at an environment with extensive growth, extensive respiration, substantial mixing, which is typical of most brackish areas, then probably you don't need that low an uncertainty that needs the application area. And if you can make do with a larger uncertainty and still make technically correct decisions, you can do it cheaper. You can do it quicker. All these things fall into place better. So you always need to think about your question. How good is good enough? Because if your goal for brackish waters is to do it as well as open ocean marine chemists make the measurements, you're probably going to disappoint yourself. You shouldn't be disappointing others, because I really don't think that's a necessary way to think about it. A simple example. If you're trying to calculate carbonate ion concentration, the uncertainty depends on the uncertainties of all the measurements that you use in the calculation, as well as uncertainties in various equilibrium constants. This is the classical formula for that. The uncertainty, combined uncertainty in y due to measure calculated from terms x1, x2, etc., depends on the sum of the squares square rooted. So that, what are we summing here? We're summing a term that's a sensitivity factor, the dy dx, and the uncertainty in x. We can express it that way, or we can express it in relative terms. That is, the relative change in y divided by the relative change in x multiplied by the uncertainty, the relative uncertainty in x. And you have to weight this whole thing by y to make them come out the same. So when can you neglect the uncertainty in a particular parameter? Well, if you look at this, let's give you a very simple example. If one of these terms adds up to is 3, that is dy dx times u is 3, and one is 1, dy dx times u is 1, so 3 squared is 9, 1 squared is 1, the sum of it is 10. The square root of 10 is almost the same as the square root of 9. The uncertainty hardly changed because of the thinking about that uncertainty of the second parameter there. So if the total effect is about a factor of 3 different, you can neglect it trivially. A factor of 2 is probably not going to worry you too much. So that's when you can neglect uncertainty. So go on to this carbonate ion concentration discussion. The relative sensitivities when you calculate carbonate ion are approximately 1 for hydrogen ion. That is, if you've got a 1% change in hydrogen ion, you get a 1% change in carbonate ion. For total carbon, same thing. 1% uncertainty in total carbon, you get a 1% uncertainty in carbonate ion. K2, 1% uncertainty in K2, 1% uncertainty in the carbonate. For K1, it's much less. It's about 0.2. So immediately you see we can ignore K1 and we can look at these others. And now we have to remind ourselves, because we talked about uncertainty Px, Pk, or Ph. Uncertainty 0.02 is about 5%. Well, 0.02 in pH is actually not so bad. We've done laboratory studies that show that most people don't get it a lot better than that reliably. 0.02 in K2 for sure that's pretty well the uncertainty in seawater, frankly. 5% error in total carbon, that's considered horrible by most people that would buy and sell you equipment to make this measurement. So that if you're looking at this as a problem, your total carbon method doesn't have to be so stunningly good to not be the problem in your calculation here. And it's that kind of thinking about it that you need to go through as you go through your own things. Now, one of the things that I've done in the past that I think has been quite valuable, but it's also grown to be potentially problematic, is I helped edit this Guide to Best Practices for Ocean CO2 Measurements, which was based on an earlier version put together with DOE money to look at open ocean surveys. And this is the problem. These procedures were aimed at scientists making open ocean measurements, and they may not be ideal for use in brackish waters. In fact, we could probably say it's stronger than may not. They are not ideal for use in brackish waters. For open ocean, you wanted it highly precise. You really didn't care how much it cost to do. It would be nice if it was cheaper, but you know, it's not a major concern. You're already spending so much money on having a ship in place to collect the samples that making sure you measure them correct was the key goal. For brackish waters, the emphases change, and I think there's still a need for more thought about how to describe measurements that people can use in brackish waters effectively and well enough for the science they need to get done. So my recommendations: for salinity greater than 20, just treat it as seawater. Of course, you may need to just check, if you're using alkalinity, that there really is no substantial organic contribution to alkalinity. A DOC would give you some feel for this, because only a small fraction of DOC is ever likely to be acid-base species. You can, the way it's traditionally done is you calculate that carbonate alkalinity piece from a measurement on alkalinity and thinking you didn't need to worry about organics and calculate the other terms, and you compare that to the same term calculated from total carbon and pH. And you see immediately if there's a mismatch, or you can, and so that's usually the way people have done it for seawater, but it's not so big a problem in these higher salinities. As we come down in salinity, the only constants available are those ones from Milero et al. Now, the Latin quote is kind of a spoof. It means basically take them with a grain of salt. Be appropriately skeptical. Just because they exist does not make them perfect. It doesn't necessarily make them imperfect. But you saw the kind of scatter there was relative to other measurements. You can't assume that the line going through that necessarily is a much better version. Potentially the most accurate combination is if you measure PCO2 and total carbon. The reason I say this is because pH measurements are not well defined in that region. But don't get greedy. I mean, the constants aren't that well defined either. So pushing to get your PCO2 precisions down to 1% and your total carbons down to 0.2%, which is possible with equipment, probably is not a helpful use of your time if you're then going to go and do a calculation with it, because there's going to be uncertainties in that calculation. Research, as I said, is going ahead to improve pH calibration for salinities less than 20, and once that's complete, my recommendation would likely change to pH and total carbon, because pH is a lot less trouble to measure than PCO2. But at the moment, you can measure it, you just don't actually have, you end up implying larger errors in the constants. For the low salinity end, well, your only choice really is to do it like we did above, but you're going to have larger uncertainties in the constants. Even though Milero extrapolates to an ionic strength of 0, salinity of 0, and even though the numbers at 0 are actually well defined, the numbers at salinities of 1 and 2 are almost certainly quite poorly defined. So you're going to have some difficulties. So take-home messages: don't follow open ocean practices blindly. consider when the assumptions that are implicit in open ocean approaches will be inappropriate in brackish systems, and choose appropriate target uncertainties for your measurements. Thanks for listening.
Thank you so much, Andrew, for that great presentation. We're going to open the floor for questions now, so please type those into the questions, or please type questions or comments into the questions control panel. And while we're waiting for those to come in, Andrew, well, I'll ask you first question. What is the best way to currently measure pH at salinity of 5 to 20? Do lab grade probes have any value?
The problem is, how are you going to calibrate pH in that region? And the approaches for seawater have varied between calibrating against a salinity 35 buffer, which is sensibly known what the pH is. You could make such a buffer for a lower salinity. It will be less accurate than made in seawater. So I think you've got two possibilities. Either you're trying to get a pH that's related in some way to what you hope is a hydrogen ion concentration so that it would work with the Malero et al. Constants, or you end up doing a pH which is calibrated on the conventional low ionic strength buffers, the phosphate buffers, the phthalate, the so-called pH 4 or pH 7 buffers. If you do the second, which is very convenient to do, and you will get reasonable precision, the difficulty you have is working out how to convert that to a hydrogen ion concentration. And at the moment, although there are ways to do that crudely, they're not well published and well studied.
Okay, Andrew, are you ready to go on to the next question?
Sure.
Continue.
Yeah.
Okay, so the second question, thanks you for the presentation. The remarks that it's a little bit dismaying. And so the question behind this, someone really wants to get in touch. All right, so here's the question. Can we have any confidence in carbonate measurements that have been taken to document trends? And I'm guessing this means in brackish waters.
If you already have confidence in the carbonate measurements, that is, that they're done the same way today as they were done 2 years before, and that if they had had the same water sample, they would give the same answer, then yes, of course, such trends are meaningful. The scientific interpretation of it, of course, depends on what you're measuring, quite, how relevant it is in a spatial distribution as well as in time. But the difficulty is often people have not thought about how well they can ensure that their analytical process is working well over protracted periods of time. If that is okay, then of course these are meaningful. And even if you measured a pH, if the salinity is the same, measuring the pH will show a change in pH that's interpretable. But it won't tell you what the pH is to allow you to interpret it. Kind of slightly across purposes there, but you can see meaningful changes even then.
Great, thank you. So the next question is, you talked about estimating the amount of organic acid present at 0 or close to 0 salinity in flowing water. Wouldn't it be reasonable to assume that organic acid could not be present in great amounts, similar to open ocean water? Isn't the problem just in the middle salinities or where residence times are higher?
There are two primary sources of organic acids that people have talked about. One are from phytoplankton growing in blooms like that. And there, clearly, it's dependent on the residence times because they can move away from that area and get mixed out. But there are also locations, and the classic example is, for instance, in the regions of Georgia and things, where the rivers themselves have high organic loadings, high dissolved organic loadings, lots of humics and fulvics. And then you will have a significant contribution. I think the numbers I'm thinking about from a paper of Wei Zhenchai from a number of years ago is up to 100 micromoles per kilogram of contribution to alkalinity from the organic materials.
Great.
So you can't rely on it. You have to check it.
Okay. Here's another question related to your last webinar. Which pH scale is most appropriate for brackish waters 5 to 20 PSU?
The Millero et al. Constants are defined on the seawater scale, I believe. That is, they have fluoride and sulfate included in. The difference between the two scales in seawater is about 0.01. As you go to, half seawater, it would be 0.005. So probably largely immaterial, but they still have the sulfate in, and that's still a relevant piece in that brackish region there. So I think your goal at the moment is still to come up probably with that total hydrogen concentration, because if you're going to use it in a calculation, you're going to use it with those constants.
Okay, a similar question. What is the best equation for total borate concentration? Upstrom, 1974, or Lee et al., 2010?
I think the answer there is that you don't know. They're a few percent different. The Lee et al. Ones are a more extensive study, but knowing the uncertainty of the measurements is very hard to do. And I don't think either paper really give you the information that makes you say, yes, these people fully understand all contributions to uncertainty in that paper. I have heard anecdotal comments that, well, if you use the Lee et al. Ones, then the consistency of the CO2 system is a little bit better. But I would point out that when you talk about consistency, it means you have to have the constants accurate, the measurements accurate, and the boron accurate. The chance of it all happening all at the same time, I think, is small. So my opinion there is, my comment there is, I don't know. I tend to use these days the Lee ones just because those are considered conventionally appropriate, but I'm not sure that it's a meaningfully better number. The standard reference composition of seawater, which kind of just about predates the Lee ones, used the other version, the Upstrom ones from 1974.
Great, thank you. And another question, which I think you addressed a bit. For river water, how much does its composition affect K constants?
It's not so easy to say that, because you've got to say, if we look at this picture, and if you're still looking at my screen, this will show the concentration of the concentration at which you have river water on this plot varies, because the ionic, river water's ionic strength can be quite small. Let's say such that the square root would be about 0.05. And so you can see there that you're really quite close to the y-axis. But there are some rivers that have significantly higher ionic strengths, particularly if they've got a lot of carbonate in. And so then it creeps around. But you're going to have the problem is, as you're in that region, is where it really starts to matter what your river water composition is. Because in seawater, you've got a 5-to-1 ratio approximately of the magnesium concentration to the calcium concentration. And that dominates what the value for K2 is, because the interactions between calcium and magnesium and carbonate ion affect the value of K2. In a river water, often that will change around, and you'll have significantly more calcium than you do have magnesium. And so its implications for K2 are meaningfully different. Again, it's anchored at 0. The K2 will have the values shown on this plot. But the direction the line takes in that small difference between 0 and 0.05 is really not well defined. And that's why I said, you know, I suspect you're coming for uncertainties of the order of 0.1 in pK2 there.
Great, thanks, Andrew. And I think with that, we're going to end up ending the webinar. And if we did not get to your questions about the content of today's presentation, feel free to contact Andrew via email. And you can find his email in the right-hand side of your control panel in the chat box. Please direct any questions about the Interagency Working Group on Ocean Acidification to me at shallenbush@noaa.gov. So thank you very much for attending this Interagency Working Group on Ocean Acidification webinar. We welcome any feedback, further questions, or suggestions for topics for this webinar series. You can submit input to me by email. You can submit input by emailing us. The link to a recording of this webinar and a PDF of the presentation will be available on the Interagency Working Group on Ocean Acidification's website in the future. Thanks again to Andrew for his very informative presentation, and to all of you for your thoughtful questions and taking the time to join us. This is the end of today's session.